So when we look at this ratio and let's try to compare these two ratio. You see the limit of this whole thing is equal to this limit. All we do really is just divide both top and bottom by x. So it doesn't change much of its essence. So we can say that the limit of this new transformation, you can call it, is equivalent to 0 over 0. So what does that mean? It means that we can apply logical rule for this new transformation. So let's go ahead and do that and see what we can get out of this. So let's just erase this part. So we apply this logical rules for this new ratio that we just have here. What do we have? We know that this taking derivative of the numerator, this is a constant, so that's 0. This is a quotient, right? You can think of this as minus inverse tangent x times 1 over x. So 1 over x will be a function, and you would have, instead of have quotient rule, you have a product rule. So that's somewhat easier, or at least for me, I think that would be more manageable. So you apply product rule for this. What do you have here? This is minus. You can leave the minus sign out here. So inverse derivative of inverse tangent x, that will be 1 over, because 1 over x, we keep 1 over x, right? So we say 1 over x times 1 over 1 plus x squared, right? Okay. So now we apply for the, so this is our first entity, okay? The second entity is 1 over x, so we apply derivative for that. So you would have minus 1 over x squared times over x squared times inverse tangent x. Okay. All right. So over derivative of sin x is cosine x. Okay. So so with this being said, what can we say about this? You can see that the limit x approaches 0, cosine x approaches 0, that approaches 1, right? So that approaches 1. And 1 over x times 1 plus x squared, x approaches 0, that's 1 over 0, so you have an infinity. So infinity, right? You have a minus here, you can put the minus out there, and look at this part right here. Inverse tangent x over x, x approaches 0, you can see that this by itself has an indeterminate form. When you see the inverse tangent of x, if x approaches 0, inverse tangent of x will be 0. And x by itself approaches 0 will be 0 as well. So you have a 0 over 0. That would be indeterminate form as well. So you can apply logical rule for that individually. But I think with enough practice, you can see or you can tell that that limit will approach infinity. So we would have inside here is minus parentheses infinity minus infinity. So you have you can say that infinity minus infinity common as we learn it, as we learn logical rule, and it's indeterminate form. But it occurs sometimes when you have to deal with complicated problems that may show up. So when you see this kind of thing, how do you go about and tackle it? There's no really, not a lot of common method to do it. But it turns out that you can compare its ratio in order to determine whether this difference right here converge or diverge. With that being said, you can treat this as in a general case, we can represent this entity as some b, and you can represent this some b of x, and you can represent this entity as a of x. So by looking at the ratio of these two entities, you can write something like this. You can write the limit at x approaches to some constant c, b over a, right? bx over ax. If this limit equal to some constant L, right? As long as L equal to 1, then the limit of its difference, meaning the limit x approaches c, bx minus ax, will approach will be converged. Okay, so by saying converge, we can, it's not really telling us anything specifically about its value, but we can at least locate or determine that it's not infinity, or it's not something that we cannot evaluate. So how do we define its value? You can either look at the initial value of each function, and you can say, oh well, what happened to b of x as x equal to c? What happened to a at x equal to c? So you can apply that and see what the value is, and the limit will be that difference. So with this particular problem, let's see what we can do here. Well, we have, this is infinity, this entity is infinity, this entity is infinity, so let's go ahead and have a look at what happened to the limit of themselves, meaning you can evaluate the limit x approaches 0, tangent, inverse tangent x over 1 over x times 1 plus x squared. Okay, what does that equal to? So if you do the differentiation of that, you will have something like this. If you do this after evaluating and after simplification and things like that, you would have the limit of this equal to the limit of x approaches 0. As x approaches 0, x squared plus 1 times inverse tangent x over x. Okay, so alright, so what do we do here? We have, after simplification, we have this. So let's evaluate what is it behaving. So at x approaches 0, 0 plus 1, that's 1. Inverse tangent of x approaches 0, that's 0. So we have 0. 0. So 0 over 0. So we know that we can apply L'Hospital rule from now on. Okay. So after I apply L'Hospital rule, what do we have? We can have, after applying that L'Hospital rule, we know that before we have down in the denominator there's an x. So after taking the derivative top and bottom, you know that down below will be a 1. So we can go ahead and cancel that. The top, however, will be 2x times inverse tangent x plus 1. Okay? So what is this limit equal to? You see that x approaches 0, 2x times inverse tangent x. That whole thing is 0 plus 1. That's a constant. So that is equal to 1. So you see L, as we talked about this before, the entity, the ratio between entity B and entity A, the ratio of them as x approaches to some constant, here x equal to 0, is 1, L equal to 1. So what does it say about that difference? you know that as they approach zero, they are both infinity. So when, and you know that as at the same time, as they approach x equal to 0, their ratio is equal to one another. So intuitively, you can think about this as two very rich people, right? If two very rich people have a lot of money, their money to some time, a certain amount of time period, they reach infinitely many quantity of they have a lot of money, just to put it that way. So and the ratio is equal to one another. What does it say is that their difference will be 0, will be approaching 0, because their ratio is approximately the same and their initial value is approximately comparable, as their infinity over infinity, and the ratio is 1. So we can, from that analysis, we can say this difference here will be 0. So with that being said, you can have this whole limit equal to the limit as x approaches 0. This we already evaluated that equal to 0. So 0 over cosine x, that will be x approaches 0, cosine x approaches 0, that's 1. So we have it 0 over 1, which is 0. So we trace back all the way here to the original problem. Turns out that the limit will equal to 0. So there you have it. 0 is the answer. So what does it say when we approach the kind of problem? How do we go ahead and tackle this, and how do we develop some sort of strategy in order to break down what we need to solve? Well, first we can look at it and see how it behaves, right? So for a certain value of x, as x approaches to some constant, as for example 0, we see here this approaches 0 and down here this approaches 0. So the first step is to evaluate what does it do, right? How does it behave? How does the whole thing act? After that, we see, oh, it falls into the indeterminate form. So we go ahead and apply L'Hopital rule, taking derivative of top and bottom. So after we do all that, if it's recurring, meaning if repetitive, you keep having the indeterminate form, it may be a good signal for you to go back at the original problem and think of other ways that you can solve it. In this case, you can simplify it. In general, you can simplify everything. When you look at the problem, you can try to simplify as much as you can and see what you can pick out from there. So you have that ratio, and you can divide top and bottom by x, so that you will get rid of this product right here. It will turn out to be one entity only, one function only. So you don't have to apply the product rule. So after you have this, you see, oh, it's still equivalent to this form. Maybe I can try to have L'Hopital rule again and see what it do. See if I already escape the cycle of recurring or repetitive, having repetitive the indeterminate form. So after we do all this, we meet another challenge, meaning we have a difference between two infinities. And it's not really common, as we see in the regular problem that we have, for example, in the textbook or something like that. But it turns out it's something to need to be solved and need to be considered. So in order to evaluate this kind of thing, the first thing you do is to find the limit of the ratio between each entity. If the ratio, it turned out to be some L, and that L equal to 1, then you have to evaluate the initial value. What the initial value do? If they turn out to be comparable, what I mean by comparable meaning is as you evaluate to infinity, that value is finite. So at the end, the difference won't account that much. So it turns out that the limit will approach 0, and here it's just a cosine of x, and x equals to 0. That's just 1. We can sort of see that from the beginning. That's the whole reason why we're trying to get rid of the x, so that we can have some nice constant down in the numerator. So that's pretty much the strategy, and later on in the future we'll see much of this problem again, and we'll solve each problem in a more definite way, and try and deliver the best analysis that we can. Thank you very much.